Now we discuss a very important result. So say we are given a polynomial f which lies over field f, and you have this extension k over f where k is the splitting field for f. So since k is a splitting field for a polynomial, so it's just a finite extension, so you can also call this normal. So k over f, this is a normal extension. Then the automorphisms of k which fix f, the size of the automorphisms or the number of elements in this group of automorphisms of k which fix f, this is less than or equal to this degree of extension of k over f. And there is equality when f is separable. So there is an equality here when f is separable, that is when f has distinct roots. So the way this theorem is generally stated is that you have a normal and a separable extension k over f. So if k over f is a normal and separable extension, that precisely means that k is a splitting field for a polynomial f, and where f has distinct roots. So if this is normal and separable, then you have automorphisms of k over f is equal to a degree of extension of k over f. So let us start with an irreducible polynomial, and then we can consider a general polynomial like this. So say you have irreducible polynomial f, and f has degree n, and say the roots of f are alpha 1, alpha 2 all the way to alpha t. So obviously t has to be less than or equal to n. If degree of f is n, then you can have at most n roots. Now in case f is separable, then you will have precisely n roots. So if you're not assuming separability, then t would be less than or equal to n. So for any irreducible polynomial like this, we have a natural map. So f naturally embeds into f of x, and then you modulo out your irreducible polynomial, you get a field. So we denote this by f subscript f. So we are just defining this. This is just a definition. And we showed that this is precisely isomorphic to f of alpha I, where alpha I could be any one of these roots. So from here you can come to this diagram. So f goes into f of f, just like this diagram here. F goes into f of f, these two are the same, and then this you're writing as alpha I, this you're writing as alpha j, because instead of I you could pick any of these roots. So basically we are permuting two roots. So there's a permutation between alpha I and alpha j in this diagram, and this phi, if you restrict here, you just get an identity map. So this is a very important diagram. So very important diagram. So this one should always remember or keep in mind for Galois theory. The entire game is just about permuting roots, which you can clearly see from this diagram. Now this diagram naturally leads us to a concept of f homomorphism. So you have this homomorphism from f adjoin alpha I to f alpha j, and if you restrict phi to this map here, you just get an identity map. These two are the same f's, just precisely this map here. You could have put alpha j here. So more generally, say you're given two extension fields k and k prime of f. So if a ring homomorphism phi takes k to k prime and you restrict it to the base field f, you get an identity map. So here you can think of writing k here and k here, and then you get an identity map here. So then phi is called a f homomorphism, and the set of all f homomorphisms you denote as hom f k to k prime. So this is how the diagram looks like. This is the phi here, this is your extension here, this is the extension here. You restrict the phi to this map here, this will become ID map here, and these are natural embedding here, natural embedding here. That's what we are saying. There are two extensions k and k prime of f. So this phi is an element of, we write as homomorphism here f k k prime, because on f it is just the ID map. So you denote it by like this. Now if k is equal to k prime, then obviously instead of k prime we are writing k, and you denote it as automorphisms of k which fix f. So these are now called f automorphisms. So now say your k is a simple extension. Simple extension means you just adjoin one element to f to get k. So then we can interpret permutation of roots to f homomorphisms. You can clearly see permutation of roots alpha I, alpha j, and f homomorphisms. So let us make this more precise, more clear. So we are just going to rearrange this diagram. So remember this diagram, we are just going to rearrange this. So now pick up any root alpha m from here. So you pick up any alpha m from here, and then you put this as f alpha m, and this you put as ff. So we have done nothing, we have just picked up a root in this here. But now you can see if alpha m is a root of f, then you have the f isomorphism from here to here, because anyway this ff is this fx over f, and here you are putting in alpha m. So nothing much has been done. But what we have done now is, to every root alpha m, you have associated this map ff to f alpha m, which is in f homomorphism. So you have to every root alpha m, you have associated this map ff to f alpha m. So this map phi you're linking to alpha m. So for every root you have this map. So more precisely you can say to every root alpha m, so say you have this map which you put it as phi of say alpha m. So this phi corresponds to alpha m because you're writing alpha m here. Nothing much, it's just notation. So you have this one-to-one correspondence, because for every root you pick up from here, you get a square like this. So for every root you have a square like this. You just keep on changing the root. Keep on changing the root, you keep on getting different phi, and each of these phi's is nothing but a homomorphism from ff to f of alpha of that root. So notice that I have round bracket here and I have a square bracket here, but we have shown in the previous lectures that this round and the square bracket are the same in case of roots of irreducible polynomials. So if you have a simple extension like this, then we have number of such homomorphisms is precisely the number of roots, because every time you put a new root you get a new phi. So put a new root, you get a new phi. So you keep on changing the roots here, you keep on getting different phi's, and the number of roots is less than or equal to degree of our polynomial, which we have said is irreducible. So this is precisely equal to the degree of extension here of ff over f. Now if you set ff equals to k, so if you set ff equals to k, so this is the number of homomorphisms, which is equal to number of roots. So this absolute sign means the number. So this is number of homomorphisms, this is number of roots. So if you set this equal to k, you get hom f k to k, and this is precisely what we are setting as automorphisms of k over f. So this we are writing here like this, and so this is less than or equal to, this is again k over f, because you're setting that as f. And obviously roots of f are equal to degree of f precisely if the roots are distinct, and distinct roots means that f is separable. So equality holds when f is separable. So when f is separable. So with equality when f is separable. But what we have done is just a simple extension, and we have talked about irreducible polynomial. Here we are talking about a splitting field in any polynomial, so we need to do a little bit of more work to carry from here to here. But this is just translation. There is no content in it, like big mathematical content. There's nothing in it. So we still need a bit of work to translate the above into splitting field homomorphisms. So what you do is you translate your polynomial f of x to tau f of x in k of x. So if k is your splitting field, you have to take your polynomial from f of x to k of x, and the way you take it is you do not touch the x's, you just change the coefficients, and the coefficients are changed precisely how tau acts on elements of f and takes them to k. So you're changing the coefficients here, and if the roots of your polynomial are alpha I in this field f, then they are translated to tau of alpha I in k. And that's it. Now instead of talking about alpha m, you talk about tau of alpha m, and you still have the same f homomorphisms. So we will still have the same isomorphism between permutation of roots tau alpha I and f homomorphisms. And that is the end of the story. For a general f, you just need to notice that any f would be a product of irreducible polynomials. So the story carries over from here to here. So you have, for each irreducible polynomial, you will have this, so it will hold for general f. If each of these irreducible polynomials is separable, then the entire f would be separable and there will be equality here.